By Orcun, who's a PhD student in the control group at ETH. I know he's worked through some polynomial optimization relaxations he's been working on, but today he's going to be talking more about selecting marking mechanisms in electricity.
Thank you for the introduction. It's a pleasure to be here. My name is Orcun. I'm a PhD student at ETH Zürich, and today I will talk to you about what we can achieve by using coarse selecting payments in electricity markets. This is joint work with my supervisor, Professor Meryem Kamgarpur. So the electricity markets transformed from being regulated monopolies to deregulated competitive markets in the last couple of decades. And these markets are different than the other markets because of the underlying physical constraints. What I mean is that they need to ensure the stability of the grid, which is the supply and demand balance at every time instance, because we cannot efficiently store electricity. Since we introduced a lot of renewable energy sources to the grid in the last decade, this task is getting even harder. And right now there are many markets running at the same time trying to ensure this stability. Today I will be mainly looking at two of these markets. First of which will be the control reserve markets. Control reserves are ancillary services that get activated whenever there is an imbalance in the grid frequency. And there are different types of reserves depending on how fast they are to deploy. There is a primary reserves that are the fastest ones, and then it goes secondary and tertiary. On top of that, there are different types of reserves depending on their direction. Some of them increase the production, some of them reduce the production, so there are also different products as such, like negative tertiary and positive tertiary reserves. Today I will mainly be looking at the Swiss reserve market, which is a weekly and a daily market for secondary and tertiary reserves. And to ensure stability, this market involves a probabilistic dimensioning criteria for buying reserves. Second market that I will look at will be the wholesale electricity markets that considers the physics behind the transmission network, for instance the ones used in North America. In this case, the transmission network consists of nodes connected to each other with some constraint lines. Some of these nodes will have generators participating in the market, and the central operator will try to meet some demand while some Kirchhoff laws are satisfied. Here the different supplies in the markets, different type of supplies in the market will be active and reactive power injections, but on top of that, power injections at different nodes will also be treated as different type of products. Whenever we're designing any of these markets or some other electricity markets, the property that we would like to achieve is the property of efficiency, or it also appears as the property of maximum social welfare. And we know that we can achieve this property if the market is immune to strategic manipulation. So today we're going to look at the following questions. How should we design electricity markets such that we can eliminate strategic manipulations and achieve a stable and an efficient grid? So here's my outline. I'll start by introducing a very general electricity market framework. Then I'll define coalition proofness as a way of being immune to strategic manipulations. And then we're going to look at the relation between coalition proofness and the tool from coalitional game theory called the core. And using this, I will define core selecting payments that attain coalition proofness property, and we will look at their relationship between these payments and the competitive equilibrium theory. And finally, I will design some core selecting payments with additional desirable properties such as budget balance and incentive compatibility. Then we'll have some numerical results. So let's start with the electricity market framework. Many of these markets that I previously told you about, wholesale electricity market, control reserve markets, they're generalizations of reverse auctions. So what I mean is that the set of participants are the central operator and the set of bidders L. Each of these bidders will have some true cost for producing electrical power, but they will be able to freely report whatever cost they want in terms of a bid, and then the central operator will collect these bids as a bid profile and will pick a mechanism, and this mechanism will define how much to buy from each bidder with an allocation rule and how much to pay to each bidder with a payment rule. This is a game theoretical framework in the sense that now I can define the utilities of the bidders and the operator. For bidders, the utilities will be quasi-linear. They will be linear in the payment. It will be given by payment minus true cost. And for central operator, it will be given by minus the total payment, because the central operator is trying to minimize its total payment or maximize this term. So now I will look at the allocation rule first, and then I will look at the payment rule. In most of the electricity markets, the allocation rule will be given by some optimization problem. To define that optimization problem, I'm going to give a functional form to the cost functions. So first of all, let there be T types of products in the electricity market. Then the cost function will have a restricted domain XL, which is a subset of the T-dimensional non-negative orthant. Here the XL will be the production constraints of that generator. I'll further assume that it is 0 at 0, which will be satisfied in control reserve markets and day-ahead markets with startup costs. And whenever this assumption is not satisfied, the following results will still hold, but under some small modifications, which I'll be happy to talk about offline afterwards. And we will have a reported cost, which is the bit. And this can have a different restricted domain, and it can have different values. It's not necessarily the same function as the true cost function. Then the allocation rule will be given by the following optimization problem. We're going to minimize some of the reported cost plus a secondary cost term. For instance, in the two-stage markets, when we're solving the market at the very first stage, we need to consider the prices that may occur in the second stage of the market. For instance, in the weekly market, we consider also the expected daily prices that may occur, and there Y would be how much we expect to buy in the daily market, and D would be the expected daily prices. And we have some general constraints, which could be probabilistic security guarantees. It could be power flow constraints as well. So next, I'll just update the previous framework with the allocation rule. Now, instead of central operator, we have this optimization problem, and the payments are also defined from the bit profile to reals. And I'll also update the utilities, which will be now given by payment minus true cost, but evaluated at the allocation rule. And similarly for central operator, it will be given by minus the total payment minus the second stage cost. We see that the payments directly enter into bidders' utilities, so the bidders will strategize around these payments. So from now, for the next step, I'll take the allocation rule as given, because it is a stability guarantee, and we would like to satisfy that, and then design payment rules with desirable properties. So what will be those desirable properties? First of all, I'll have the individual rationality property, which also appears as voluntary participation, cost recovery, revenue sufficiency for bidders. In different frameworks, it appears differently. So it would mean that the bidders should face non-negative utilities. And the main property, the second one, is that I would like the payments to achieve efficiency, which means sum of all utilities should be maximized. And because of the way the utilities are maximized, we know that we can achieve this property if we can compute the allocation rule under true costs. Related to this, I'll define dominant strategy incentive compatibility, which in this presentation I will just refer to as incentive compatibility for simplicity. This would mean that truthfully reporting your cost is your dominant strategy for every bidder. Clearly, if the market has this property, we would be able to remove all the possible unilateral deviations from the market. So let's look at some widely used payment mechanisms. So we have pay-as-bid mechanism, which is used in some of the European balancing markets. And clearly, if you get what you report, a rational agent would just overbid to ensure profits. So this is not incentive compatible, it is not efficient. And next, we're going to look at the locational marginal pricing mechanism, which is generally used when you have an optimal power flow problem. In this case, each bidder is set a nodal unit price, which is the Lagrange multiplier of the nodal balance equality that this bidder is associated with. This mechanism relies on competitive equilibrium theory, so we have the following property. If each bidder is a price taker, what it means is that if each bidder believes that they cannot affect this, if each bidder believes that this Lagrange multiplier is independent of their bids, then this mechanism would be incentive compatible. There are two criticisms. First of all, this is a strong assumption not found in practice. There are manipulations in general risk the stability of the grid. In an LMP mechanism, you can maximize your profit by reducing your maximum supply and inflating your bids. And secondly, this economic rationale relies on strong duality. But if we consider a realistic electricity market model with unit commitment decisions and AC optimal power flow, we may not have strong duality, so we may not be able to come up with meaningful Lagrange multipliers. And all in all, we have individual rationality with both of these payments, but we don't have efficiency and incentive compatibility properties. So, as an alternative, I'm going to look at the famous Vickrey-Clarke-Groves mechanisms. Just a second. To do that, I'm going to define a restricted optimization problem. This JB minus L will be the market objective. When bidder L is removed from the market, clearly it will give a higher objective value than the problem on the right, because solution to the problem on the left is a suboptimal feasible solution to the problem on the right. Then the VCG payment will be given by externality, which is the difference between these two terms. So the one on the left is cost of other bidders in the absence of L, and the one on the right is cost of other bidders when L is present. It is like a marginal contribution term. And a straightforward generalizations of works of Vickrey-Clarke-Groves to the case of continuous goods, second stage costs, and general constraints, we have the following. The VCG mechanism is incentive compatible. Since it is incentive compatible, I'll assume that every bidder is just implementing their dominant strategy, which is truthful bidding, and then this mechanism is efficient, and on top of that, this mechanism is individually rational. So since this mechanism exists even in the non-convex case, so the only assumption I need is that this problem is feasible, which is a practical assumption in the electricity markets. Since also it achieves exact incentive compatibility, recently it was proposed for a broad class of electricity markets. But there is a reason why this mechanism is called the lovely but lonely VCG mechanism. To see that, we're going to look at the following example. We're going to have a DC optimal power flow problem with 4 nodes. 3 of the nodes will have generators with convex quadratic costs, and the central operator is trying to meet the demand at the 4th bus while satisfying some line constraints and Kirchhoff laws. So when we solve this market, we see that only generator 3 is winner. So it's the only one that is allocated a quantity, and here is its payments and utility, and we can conclude that truthful bidding is the dominant strategy. But the VCG mechanism gives rise to coalitional manipulations. Now bidders 1 and 2 can collude and just bid zero curve. They would become the winners, and on top of that they will make profits. And another concern here is that for central operator, you can see the total payment increased as well. So actually there is another property that we desire. I'll call it coalition proofness, which means that the joint deviation should not be profitable for losing bidders, and bidding with, and this is collusion for losing bidders. This is called collusion for losing bidders. And second one is bidding with multiple identities should not be profitable for any bidder, and this is shield bidding. The second one, in this presentation, I will not be able to give any examples, but it is quite problematic. About the first one is only for losing bidders, because there is the case that no mechanism can eliminate. It's the case where all bidders agree and they just inflate their prices, and there is no payment mechanism that can eliminate this situation. So it's only for losing bidders. So next, we're going to characterize this desirable property, the coalition proofness property, and to do that, I'm going to bring a tool from coalitional game theory called the core. So the core will be a restriction on the utilities with respect to the submitted bids. So I'll define that as revealed utility. It will be defined as payment minus submitted bid evaluated at the allocation rule. So if we believe that the bidder was truthful, this is how we would compute its utility. And similarly, central operator's revealed utility will be just exactly its utility, and it will be given by this term. And now I'm going to also define a more general restricted optimization problem. This will be the objective value under set of bidders S. You can see that I removed all the bidders that are not in the set S. Let's keep that in mind. Now I'll define the core. Core will be given by as set of revealed utilities that cannot be improved upon by forming coalitions. To be more exact, it will be this polytope. So for bidders, this polytope, we restrict them to the non-negative orthant to ensure individual rationality property. This equality constraint means that sum of revealed utilities is maximized because the term here is minimized. So this is efficiency with respect to the submitted bids. And the last set of constraints says that there is no blocking coalition, which translates into following. There exists no set of bidders S that would make a deal on their own, from which they would share this total utility and be better off than their current situation. Even now, because of the way this is defined, we can see that there will be relationship between this constraint and the coalitional manipulations. And next, I'm going to define a core selecting payment rule, which will be defined as follows. It will have a pay as bid term and the revealed utility term, and these revealed utilities will always lie in the core. And now we can show that core selecting mechanisms are exact class of coalition proof mechanisms. There are two main observations that we can make here. First of all, pay as bit is a core selecting mechanism. So if we give revealed utilities of 0 to everyone, you would end up with pay as bit mechanism, and we can show that this point lies in the core. And second one is that core selecting payments are always upper bounded by the VCG payments. The reason is as follows. The maximum value at each bidder coordinate of the core polytope is exactly given by the VCG revealed utilities. So when you make core selecting payments, there is no way you can end up with payments that are larger than VCG payments. So in the previous example, we saw that the VCG mechanism was not coalition proof for a very specific instance with convex quadratic costs and the polytopic constraints of DC optimal power flow. To understand this better, we're going to first look at the following question. For which markets can we ensure that the VCG mechanism does not suffer from this problem? And we see that to achieve this property, we need a special type of polytope, which is a polymatroid. I'll define this T in brackets to be the set of type of supplies. Then, actually, we will need a contrapolymatroid, and I'll define a contrapolymatroid as a polytope defined by a supramodular function. In its most generality, it will be given by this set of constraints. For bidders, we'll have production capacity constraints, and for the operator, we'll have procurement requirements for different subsets of types, and this requirement will be given by some supramodular function. And then we can show that if the bids are convex and separable, and the constraint set is a contrapolymatroid, we can show that the VCG mechanism is core selecting. How does the proof work? So using the idea that the greedy algorithm is optimal over a contrapolymatroid, we can show that the objective value of this optimization problem as a function of the set of bidders is supramodular. And using the supramodularity property, we can show that the VCG outcome always lies in the core. This is related to a study in economics on gross substitutes valuations, and it actually extends that to gross substitutes constraints. I would be also very happy to talk to you about that if anyone's interested in that. And we see that optimal power flow problems, control reserve markets do not satisfy this restrictive condition. And this is the reason why the VCG mechanism is in general not core selecting in electricity markets. So to illustrate it more, we're going to look at the two bidder case. So for two bidders, I illustrated the core. Core is a polytope on the revealed utilities, and the maximal coordinate is given by the VCG revealed utilities. And in general, when we form this VCG outcome, we see that this outcome does not lie in the core. This maximal point is not in the core. With this, we conclude the coalition proofness analysis of the VCG mechanism. And now we're going to look at the following: is the LMP mechanism core selecting? And to study that, I'm going to bring competitive equilibrium theory. Just a second. So, to define competitive equilibrium, I'll define price functions, PCL, that map from the supplies to some prices. Then I will say that an allocation and a set of price functions constitute a competitive equilibrium if these two conditions are satisfied. First condition says the following: if we assume that the payments are formed from these price functions, the allocation maximizes the utility of the bidders, because utility of the bidder is given by payment minus true cost. And similarly, second condition says that the allocation rule minimizes the total payment of the bidder. In other words, maximizes the utility of the operator as well. I would like to highlight that these price functions are not game theoretic solutions. These are just set of consistency conditions that would model how payments would be formed from economic interactions. And the way we define here actually extends the traditional definition, the valuation equilibrium, which is given by linear prices. But I want to highlight that here this PCL can be bidder dependent, and it could be nonlinear. Using these two conditions, we can easily show that competitive equilibrium is always efficient. What I mean is that it only exists for the allocation rule under true costs. So from now on, when I look at this definition, I'll restrict my attention to the x star of C. And this is also related to the first welfare theorem. So here we're designing payment mechanisms, and payment mechanisms do not give rise to price functions. So how can we attain a competitive equilibrium with mechanism design? And to understand that, I'm going to bring in a definition. We will say that a mechanism ensures the existence of a competitive equilibrium if for any admissible cost profile there exists functions PCL such that when these functions are evaluated at the allocation rule, we get the payments, and this price functions and the allocation constitutes a competitive equilibrium. Let's, to understand this better, bring in the LMP mechanism. So the LMP mechanism under strong duality will satisfy this requirement with these price functions. Here the lambda star concatenates the Lagrange multipliers of the nodal balance equalities for active power injection, and you see that the dimension here is T, because in this market the types of products are just the active power injections at different nodes. And as a remark, this will set a linear price for each supply type. So actually, this is not a bidder-dependent payment mechanism. It just depends on the supply type. Now I will update the definition with the price functions of the LMP mechanism. And here we see that actually the first condition is equivalent to the price taker incentive compatibility. Because if a bidder treats lambda star S, C to be not depending on its payment, on its bid, that bidder would be willing to bid truthfully because the truthful allocation maximizes its utility. And now I will bring our main result, which shows that course selecting mechanisms are also the exact class of mechanisms that ensures the existence of a competitive equilibrium. One direction of the proof follows from forming suboptimal feasible allocations such that we show that the core constraints are satisfied, and the other direction of the proof follows from forming price functions of this form. I want to highlight that these price functions are totally totally depend on the bits. They're bidder dependent, and they're highly nonlinear. But what this proof says is that course selecting mechanism actually extends the economic rationale of the LMP mechanism to nonlinear prices and bidder dependent payment. This result extends the line of works from Shapley, Shubik, and Bikhchandani and Ostroy. The first work, Shapley and Shubik's work, is for house allocation problems where there is a unit demand and unit supply. And the second one by Bikhchandani is a package exchange problem. So our work, as opposed to those works, we have more general constraint set, we have a continuous good, and we have second stage cost. So there are several implications of this result for the LMP mechanism. So now we can say that the LMP mechanism is course selecting and coalition proof because it ensures the existence of a competitive equilibrium. And we can also say that VCG payments always upper bound the LMP payments because VCG payments upper bounds competitive equilibrium prices. But we know that the LMP payments may not be applicable to the general setting. And in that case, we can say that the course selecting mechanisms always exist, even under non-convex widths and non-convex constraints, so they will always be viable payment mechanisms. Since course selecting mechanisms have this desirable property, we will look at how we can design them such that we can achieve additional properties such as incentive compatibility and budget balance. So I'll start with incentive compatibility. It is well known that the VCG mechanism is the unique incentive compatible mechanism that makes the least payments. Since course selecting mechanisms in general pays less than the VCG mechanism, they don't have the incentive compatibility property. And on top of that, there are many points to choose from the core. Even the pay-as-bid mechanism is a course selecting mechanism. So next we're going to look at the following question. Can course selecting mechanisms approximate incentive compatibility without the price taking assumption? To understand this, we need to first define what it means to lose incentive compatibility. So to do this, I'm going to bring the following lemma. We'll quantify the violation of the incentive compatibility under any course selecting mechanism. So what this lemma says is that the maximum gain of any bidder by a unilateral deviation under course selecting mechanism is given by the difference between the revealed utilities under the VCG and the revealed utilities under the course selecting mechanism. So in other words, the closer you get to the VCG payments, the better you approximate the incentive compatibility. And now, using this idea, I'm going to define the maximum payment course selecting mechanism. Here, the revealed utilities of this course selecting mechanism will be computed via this optimization problem. We're going to maximize the sum of the revealed utilities, and then as a tiebreaker, we're going to pick the one that is closest to the VCG outcome. And invoking the previous lemma, we can say that this mechanism will minimize the sum of maximum gains from unilateral deviation among all course selecting mechanisms. One thing to highlight here is that this constraint is exponential in the number of bidders. Because when you want to characterize the core, you need to evaluate the market under all possible subsets of bidders. Fortunately, this problem has been well studied in coalitional game theory framework. So it can be tackled via iterative constraint generation. So in practice, we can solve this problem by just generating, let's say, 4 or 5 of core constraints. This was a method that was first used by Danzig to solve big linear programs, and as far as I know, this is the first paper that used this to compute a core outcome in coalitional game theory framework. And now I'm going to go back to the previous illustration and I will update that. So we have the core and we have the VCG outcome, and the MPCS outcome is the projection of the VCG outcome onto the core given by this point. And assuming that the LMP exists, LMP mechanism will be some other outcome in the core. I put that there intentionally because in the numerics we see that the LMP mechanism sometimes for some bidders it ends up with larger payments, and for some bidders it ends up with smaller payments. But all in all, what we can say is that the total payment under MPCS mechanism will always be higher than the one under LMP mechanism under the same set of bids. But of course LMP outcome may not exist, may not be applicable. So to highlight, this mechanism does not rely on price taker assumption, and on top of that, if the VCG outcome lies in the core, the closest point to the VCG would be the VCG itself, so VCG would be the MPCS mechanism. In return, the payments will be nonlinear and they will be bidder dependent, which would be a big shift in many of the electricity markets. I want to highlight something here about the bidder dependency. These payments are bidder dependent, but since course selecting mechanisms are coalition proof, bidder dependency is a bidder cannot manipulate the bidder dependency by bidding with multiple identities. At least we have some sort of a guarantee. Of course, fairness-wise, bidder dependency is quite problematic. And next, I'm going to extend our model to the exchanges very briefly, and which has a subset two-sided markets. In this case, demand side will also provide bids. So for the allocation that they receive, demand side will provide payments. And in this case, we have another important property, the fact that the central operator should not end up with deficits. And that's called budget balance, and we'll look at whether the MPCS mechanism achieves this budget balance. So the exchange setting will relax the domains of the cost functions from non-negative Orton to three-dimensional reals, such that we can encode bidders that are not only supplying but also trying to buy electrical power. And as soon as we relax the domains of the supply, all the previous results I discussed will extend to the exchange setting as well. For instance, the coalition proofness and competitive equilibrium results. And then budget balance is the property that the central operator faces non-negative utilities, which is given by this one. And it is well known that the LMP mechanism is budget balance, and whenever it ends up with budget surplus, it also provides us ways to reallocate this budget through congestion rents and financial transmission rights. But on the other hand, we know that VCG mechanism is not always budget balance, and this is a result of the famous Meyerson and Satterthwaite impossibility theorem that says no mechanism can always be budget balanced, efficient, incentive compatible, and individual rational. And our result in this part says that any course selecting mechanism is budget balance. So when we are designing course selecting mechanisms, budget balance would not be a concern. This proves the budget balance property of the MPCS mechanism, but it also provides an alternative proof to the fact that the LMP mechanism is budget balance. With this, I would like to look at some numerical results. First, I will look at an AC OPF problem with a non-zero duality gap, and then I will look at Swiss reserve market, and finally I will look at a two-sided market with DC optimal power flow constraints. So I'll start with the AC OPF problem with a duality gap. This is a problem, it's a market problem based on the 5-bus model provided in paper of Buch. Oh, I'm hoping that I said it correct. So this is a 5-bus network. There are two generators providing convex quadratic costs. We have AC optimum power flow constraints, and we're trying to meet the demands at second, third, and fourth buses. For this problem, we can show that the SDP relaxation is not tight, so there's a non-zero duality gap, so Lagrange multipliers may not be meaningful. Fortunately, this is a polynomial optimization problem, so we can solve it to optimality. In this case, we can solve it to optimality with the second level of moment hierarchy. So here is the market outcome. So these are the convex quadratic costs. Here are the optimal allocations. Since LMP is not applicable, I gave the pairs with outcome, so we can compare it with MPCS. The important observation here is that the VCG mechanism was core selecting, so MPCS outcome was equivalent to the VCG mechanism. So it also attained dominant strategy incentive compatibility and efficiency property. Another thing to highlight is that having a non-zero duality gap does not imply the fact that there exists no competitive equilibrium in linear prices. But in this case, we can prove that there are no linear prices that would constitute a competitive equilibrium just by using the tools that we previously introduced. Here is the logic. So since the bids are strictly convex, to have a competitive equilibrium in linear prices, for bidder 1, we should set the marginal cost as the linear price. If we do that, we get $53.2 per megawatt. And this yields the payment 13,000. This payment is clearly larger than the VCG payment, so it cannot lie in the core, so it cannot be a competitive equilibrium. So with this method, we can prove that there exists no linear prices, there exists no competitive equilibrium in linear prices. The second example will be the Swiss reserve procurement auctions. This is a two-stage stochastic weekly market that also has a daily market as well, but we're going to look at the weekly market here. So in this case, mutually exclusive bids are submitted. So the bids are set of price and quantity pairs, as there are some bidders who submit even 60s and 70s of these. So at the end, we get a model like the following. Here, X is the power to be purchased in the weekly market, and Y is power we expect to purchase in the daily market. And D is the expected daily market cost. The constraints are polytopic, and they define the following requirement. The requirement says that the reserves should ensure a deficit probability of less than 0.2%. This is partially based on some requirements and some past data. And we're going to solve an instance of this market from 2014 where there are 67 bidders. Linear prices are not applicable in this setting because it's highly non-convex. And we get pay as with pay. Sorry, I should have also said that this mechanism is right now run by the pay as with mechanism. And this would have been the payment of that week in 2014. And we see that the MPCS mechanism makes less payment than the VCG mechanism. So it means that the VCG mechanism would not be coalition proof because the outcome is not in the core. What I want to highlight in this example is that even in the case where there are many bidders, we see that the MPCS mechanism can be computed in a similar time as the VCG mechanism. So if the VCG mechanism is computationally feasible, so is the MPCS mechanism. Finally, I will look at a two-sided market with DC optimal power flow constraints. This is the previous example with a couple of tweaks. The main tweak is that now the demand is also elastic and it is participating in the market, and also tightened up this line constraints a bit. And now we're going to look at the budget balance under different mechanisms. So we see that the pay as with mechanism ends up with $48.3 budget surplus. LMP mechanism ends up with $2.8 because these two lines are tight at the optimal solution. These constraints are active. But the LMP mechanism would give us ways to reallocate this budget surplus using congestion rents and financial transmission rights. In the case of the MPCS mechanism, we end up with strong budget balance, which is 0, and the VCG mechanism ends up with deficit. And with this table, we confirm our theoretical analysis. We get the result that all course selecting mechanisms are budget balance. With this, I would like to conclude. So, in summary, in this talk, we studied coalition-proof course selecting mechanisms. And we derived conditions to first ensure that the VCG mechanism is course selecting. And then we showed that these conditions were quite restrictive. And we looked at the relationship between the core and competitive equilibrium and then showed their equivalence. And using this idea, we were able to say that actually the course selecting mechanism generalizes the economic rationale of the LMP mechanism to nonlinear payments and bidder-dependent payments. We then designed course selecting mechanisms with additional properties such as incentive compatibility and budget balance, and we verified it with optimal power flow test systems and Swiss reserve market. In our papers, we have more detailed numerical results that I can refer you to. And as an outlook, right now we are looking at ways to reallocate the budget surplus in course selecting mechanisms. So as I said, the LMP mechanism provides methods such as congestion rents and financial transmission rights, and we're trying to see if we can define something similar to that in the course selecting case. For instance, there are instances where the MPCS mechanism also ends up with budget surplus. And finally, all this study was done in one-shot markets, and it is important to understand how bidders would adapt to payment rules in a repeated setting. I would like to thank you for your attention. The results on the talk, some of them appear in these papers, and I will be happy to take your questions.
Questions?
Yes, could you clarify the fact that you have a budget surplus? I understood that you have a budget balance, so.
What I mean by budget balance is weak budget balance, where we end up with a surplus. What I mean by weak budget balance is the fact that we don't end up with deficit. Is it clear?
Okay.
So surplus is acceptable.
Not zero, so okay, it's a positive stuff.
So here budget balance in the slides, what I mean was weak budget balance.
Not zero.
Yeah.
I just wanted maybe to remark, if you thought about this, like having heterogeneous payments would be valuable. I mean, a big problem today is that we have a homogeneous population, nobody's getting a thing, and they're all hoping for a crisis so that an expensive generator comes on, and then they recoup their losses. And this would be, it seems like it's a much more, it gives much more flexibility on being able to say, I'm going to keep some of these fast generators that are expensive available, and not having to pay everybody a higher price because of that. I think there are other advantages beyond what you said to be at least to convince the balancing authority that a non-uniform payments are.
That could be an interesting motive for having bidder-dependent payments. Yeah.
But I mean, yeah, it would be an additional motivation. That's one.
Yes. Yes.
It's outside the theory.
Yes. Yeah.
The computation of the VCG payments and the core can become quite intractable. Can become intractable quite quickly. Have you thought of any way of approximating those payments in a way that you can keep the desired properties?
Intractable in which sense? You mean computing the VCG outcome is intractable?
Yeah, the computation, like when, I don't remember the number, but when you exceed like 20 or 23 bidders,
Yeah.
it becomes expensive to compute the payments.
So VCG mechanism requires requires calls to the optimization problem, market optimization problem. They are linear in the number of bidders. So it's in general quite tractable. If you can solve the problem once, you can. I assume that you can solve it for each bidder.
I doubt it.
Okay. Okay.
I think it's not the case. I think
Okay.
that it's computationally intractable. But
In-
I can. We can take you off. We can take that offline if you like.
But maybe you're right. Like if it's like a case where there are thousands of bidders and the problem is highly non-convex, I guess then it will be quite hard.
Because there is this community of algorithmic game theory in which they try to approximate the payments of the BCG mechanism because of that.
Okay.
And that's one of the basic problems of it, the applicability of that. And the same goes for the core computing mechanisms, which is a practicability issue.
Mhm. I'm not familiar with that work. It would be great if we talk about that afterwards, because I would be very happy to learn about that. But here, the assumption is that the VCG mechanism can be computed, because I assume that it's linear in the number of bidders. I only need to compute the market outcome. If the number of bidders is n, I need to compute the market outcome n plus 1 times. And similarly, if that is tractable, MPCS mechanism is always almost always tractable as well, because I only need couple more market runs to get a core outcome from this mechanism. Okay, thank you. Yeah.
Could you expand a bit more on your final point on the previous slide about how you'd roll this out to multi-stage repeated setting?
So this is something that is really interesting to me. So right now, the VCG mechanism, if it is coalition proof as well, in that setting, we can say that even in the repeated setting, for the bidders, it's always optimal to bid truthfully. So they would be maybe willing to bid truthfully. But if we implement a mechanism like the course selecting mechanism, which is not incentive compatible, over the course of repeated realizations, which is quite often in the electricity markets, they would learn more about the other market participants, and they would try to inflate their bids a bit more as well. But for me, there are two ways to approach this problem. First of which is computing the Bayes-Nash equilibrium of these mechanisms under such complex non-convex setting. There are computational approaches for that. There are no theoretical approach that would apply to the Bayes-Nash equilibrium of such a complex problem. And the second one is to compute the correlated equilibrium of this mechanism under non-convex constraint, and that would be much more tractable setting. We can just pick bidders. Yes, we would assume that a rational bidder would implement no regret algorithms, and then we would try to estimate their behavior. These would be I think, the learning in repeated setting and the adaptation in the repeated setting that I tried to mention.
Any more questions? Okay, I think let's thank the speaker again.
Thank you.